Hi, everybody. It's Professor Mitchell. We have reached the last section of Chapter 3, which is 3.6 on functions. In this section, we will identify relations, domains, and ranges, identify functions, use the vertical line test, and use function notation. And when I was looking for the SLO that had the best fit with this section, I decided it was SLO-A, which in this case is going to be performing mathematical operations on functions. All right, so we start with some vocabulary. A relation is any set of ordered pairs. The set of all x coordinates of those ordered pairs is called the domain of the relation, and the set of all y coordinates is called the range of the relation. So for example, here's a relation. It contains 5 ordered pairs, 1a, 1b, 3b, 4b, and 5c. The domain of this relation is the set of all the x coordinates, or the first coordinates. I see 4 different first coordinates. I see 1, 3, 4, and 5. Notice that we only list the 1 once. Whenever you write sets, you only list elements 1 time each. And then I see 3 different second coordinates. I see A, B, and C. So that would be the range of that relation. A function is a specific kind of relation. It is a relation that assigns to each x value exactly 1 y value. In other words, one single value of x cannot go with 2 different values of y. So this particular relation here would not be a function. And the reason is because of these first 2 ordered pairs. We have the x coordinate 1 being matched with y coordinates A and B. All right, so each single x coordinate can only be matched with at most one y coordinate. All right, so here's an example. Think about this one for a minute or so. Pause the video. Which of the following relations are functions? We have letter A, 1, 2, 2, 4, 3, 6, and 4, 8. We have letter B, which is 0, 0, 1, 1, 1, negative 1, 4, 2, and 4, negative 2. And then we have letter C, which is negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. All right, so when you're ready, we'll compare notes on that. Again, please pause the video and think about it for a minute. I am going to switch over to the tablet. All right, so let's start with letter A. The easiest way to determine whether a set of ordered pairs represents a function is just to look over all the x coordinates and make sure that they are all different. All right. There's no way that you can have one x coordinate going to 2 different y coordinates unless that x coordinate is repeated in an ordered pair. So in the case of letter A, I see 4 different ordered pairs, and I see 4 different values of x, 1, 2, 3, 4. So this is a function. Letter B does not represent a function. One reason it doesn't represent a function is because the number 1 is going to 2 different values of y, both 1 and negative 1. And incidentally, you have the same problem with x equals 4 is also going to 2 different values of y. Okay, so that would be a no. Letter C, I see 5 ordered pairs, and I see 5 different values of x, negative 2, negative 1, 0, 1, and 2. So that is a yes. Sometimes students get confused because there are some repeated y values in letter C, but that's perfectly okay. All right. Okay, so we have 2 functions and 1 relation that is not a function. I can't remember if I got to this point on the slide. I don't think I did, actually. But the next thing I wanted to show you is what it looks like when you graph these ordered pairs. We're going to see something that the two functions have in common that letter B does not. Okay, so the first thing I'm going to do, and I think I only have to do this in letter A, I'm going to mark off my y-axis so that each line represents 2. That way I can get to the number 8. These can represent 1, that's fine. Okay, so we have 1, 2, 2, 4, 3, 6, and 4, 8. And although I know it's tempting, I'm not going to connect those with a line. This function contains just those 4 ordered pairs. It doesn't contain anything in between. So that's actually the complete graph. Letter B, which will just have its normal scale, is 0, 0, and then 1, 1, and then 1, negative 1. Keep in mind that these two ordered pairs being together in the relation was what kept it from being a function. And we also have 4, 2, and 4, negative 2. And then finally, in letter C, we have negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. All right, so I want to focus on letter B first. As I mentioned, one of the problems with this was 1, 1, and 1, negative 1, both being there. Notice that those 2 points lie on the same vertical line. They have the same x value, but different y values. Same thing with 4, 2, and 4, negative 2. However, that doesn't happen in letter A or letter C. No matter where you draw a vertical line, even over here, it only hits the graph at most 1 time. Okay. And that is called the vertical line test. So let's go back to the presentation. Birds are squawking in the background. Okay. So the vertical line test says that if a vertical line can be drawn so that it intersects a graph more than once, that graph is not the graph of a function. All right, so here's a quick example. Determine whether each graph is the graph of a function. Let you look those over for a few seconds. All right, I'll turn my pen on here. I don't need to go over to the tablet for this one. All right, number 1, this thing that looks like a circle, is that a function? Oh, actually, I just thought of something. Okay. That would not be a function because this vertical line, for example, intersects the graph twice. So that is not a function. How about I just put a red X under this one and we'll remember that means no. All right, letter, or actually I don't have these labeled, right? So number 2, the second one, the middle one, all right. Does this represent the graph of a function? Well, yes, this one does, right? Because no matter where you draw a vertical line, it only hits the graph 1 time. Just making sure my lines are vertical. All right, so that would be a yes, green check mark. All right, and then the last one, does that represent a function? That one does not. Actually, this reminds me a lot of our, oops, I forgot. Yeah, I have this tool for drawing straight lines here. Okay, yeah, it reminds me a lot of letter B from the last example. Okay, so there's a vertical line that hits the graph more than once. This is not the graph of a function. All right. So let's put that back on, get rid of this. All right. Function notation. So this might be the part that students have the most trouble with. It takes some getting used to. All right, so consider this relation that we talked about earlier. Contains the ordered pairs 1, 2, 2, 4, 3, 6, and 4, 8. Notice that each y value is 2 times the corresponding x value. 2 is 2 times 1, 4 is 2 times 2, 6 is 2 times 3. So you can actually write an equation that represents that function, y equals 2x. So this can also be written as f of x equals 2x. Sometimes we write f of x instead of writing y, okay? So the first thing I want you to notice about that is that I did not say f times x here. It pains me to even say that. And I know it looks like that, and that's probably part of the confusion with this function notation. It does look like multiplication. It is not multiplication. F is not a variable. We're never going to fill in a number for f. F is just the name of the function. So if we were to talk about f of 1, for example, that means replace x with 1 and find the corresponding y value. All right, so next batch of examples, we're going to find f of -2, f of 0, and f of 3 for these two functions. And then we're going to write the corresponding ordered pair for each given function value. F of 7 equals -2, and g of 0 equals -7/8. All right, here we go. So first we're finding f of -2, f of 0, and f of 3 for these two functions, starting with f of x equals 7 minus 3x. So what I like to do is to rewrite the function without the x. So write it like this, f of blank equals 7 minus 3 blank, and then fill in the blank with whatever number's there, in this case, -2. All right, so that gives me oh, geez. What happened there? Okay, that gives me 7 plus 6, which is 13. So f of -2 is 13. I'll do the same thing for f of 0. F of blank equals 7 minus 3 times blank. If I fill in the blank with a 0, I get 7, right? And finally, f of 3. So I start with f of blank equals 7 minus 3 blank. Oops. Gives me 7 minus 9, which is -2. All right, so you should definitely try letter B. I'm going to go ahead and get it set up. Okay. So I'm actually going to be starting with the tricky one here. This is one reason I like to write f of blank, because sometimes when you have a negative number there, it puts you in this situation. The square of -2 and then subtract 4. So I don't remember talking about this. I think it's probably come up in the homework. The difference between the square of -2 and this thing, okay? The square of -2 means -2 times -2, which comes out to +4. Whereas if you leave out the parentheses, that means multiply 2 by itself and then make the answer negative. So that would give you -4. Okay, so it does make a difference whether you put the parentheses there or not. Okay, so let's see. Just want to make sure it doesn't all run together here. Okay. So again, the square of -2 is 4. 4 minus 4 is 0. So f of -2 is 0. F of 0 is 0 squared minus 4, which is 0 minus 4, which is -4. And finally, f of 3 gives you 3 squared minus 4. 3 squared is 9. 9 minus 4 is 5. All right. So that turns out to not be too hard. Then we're writing the corresponding ordered pair. This is very easy once you know how to do it. Just remember that the number going into the function is x. The number coming out of the function is y. So if f of 7 is -2, that represents the ordered pair 7, -2. And the same thing for function g. The number going in is x. The number coming out is y. That ordered pair would be 0, -7, 8. All right, back to the presentation. Okay, here we go. All right, so now they've given me a graph and they have a few questions about this graph. They want to know first, what is f of 1? And then the values of x for which f of x equals 0. Then they want to know the domain of f and the range of f. And I actually have 2 examples like this, so I'm going to leave the second one for you. I'm going to ask you to pause your video and try that one when we get there. But let's do this one together. I did the best I could to draw this graph. Okay, I think I did a pretty good job. All right, so f of 1 is 1 an x or a y value? 1 is an x value, right? Because it's going into the function. So when they give you a graph and they ask you to find f of 1, that means to locate the point on the graph where x equals 1. So if I go to x equals 1 on the x-axis and I look up and down, eventually I will find this point right here, which has a y value of 3. So that means that f of 1 is equal to 3. All right, pretty easy, right? Next one, we want to find the values of x for which f of x equals 0. Is 0 an x value or a y value? Well, 0 is a y value in this problem. So I go to y equals 0, which is the x-axis, and I look for all the points where y is equal to 0, and in this case, there are 2 of them. That can happen. One there, one there. All right, so there are 2 values of x that do that, x equals 0 and x equals 4. Okay, now the domain and the range. This is something that people do have some trouble with, okay, but I have a system that I like for doing this. Remember that the domain represents the set of all x values that are part of the function. So when you have a graph of the function, those are the x values that are represented on the graph. So the way that I like to figure out what those x values are is, and this would be easier if I was standing in front of you in a classroom, I like to take the graph and squash it down onto the x-axis. All right, so let me see if I can draw this for you. So this point would get squashed down to here, and this would get squashed down to here. That would get squashed down to there. These points would get squashed up. Okay. And eventually, the squished graph would be along the x-axis. So the question is, what points on the x-axis get hit by the graph? Well, the key to that is to look at the graph and see, does it go forever to the left and does it go forever to the right? If it does, and this one does, right? So this arrow here means it's going forever down and to the right. So that means as long as you go out far enough or go down far enough, you will eventually find a point that corresponds with any value of x you want in that direction. And the same on the left side. Goes forever and ever to the left. So since all values of x are covered, we would say that the domain is all real numbers, which remember from section 2.8 can be written in interval notation as negative infinity, comma, infinity. So that's just a different way to write the answer. All right, and then the range is the same idea for y. All right, so if I were to, let me see if I can get rid of some of this scribble. Might be a little easier to follow if I don't have all this stuff here. Okay, well, that's pretty good. Let me just put these segments back. Okay, so now imagine squashing the whole graph onto the y-axis. All right, so let me switch to a different color. I'll do green this time. This point would get squashed there, and this point would get squashed over here. Actually here, all the way to there. This point would get squashed here. Okay, some of the points on the y-axis would get hit twice, right? Okay. So if I squash this graph onto the y-axis, well, I'm going to hit all of these points, right? And I'm going to hit all of these points and all of these points and all of these points, but not forever and ever and ever, because this graph has a highest point. It doesn't have a lowest point, so it goes forever in that direction. But the highest point on the graph is at y equals 4. So this point will get squashed onto the y-axis, but nothing above that point will. Okay, remember that when a particular endpoint is included on the graph, we put a bracket there. Okay, so there are two different ways you could write this answer. You could say y less than or equal to 4, or you could write it in interval notation. You could say negative infinity, comma, 4 with a bracket. All right. Okay, so I think I'll just stay on the tablet and show you the next example. Again, I would like you to try this one first. Okay, so it's got a different graph, and this time they're asking first, what is f of 5? Then they're asking for the set of all x for which f of x equals 2. And then finally, they're asking for the domain and the range. So please pause the video, try this one, come back and compare notes. All right, so I'll go through this one a little faster because I figure you've already done it. Letter A, f of 5. Go to x equals 5, which is right here. Look up and down. You notice this point is on the graph. What is the y value for that point? It is 5. So f of 5 is equal to 5. The set of all x for which f of x equals 2. Remember that 2 is a y value. I look to the left and look to the right, and I see only one point with a y coordinate of 2, and that is this point over here, which is -4, 2. So that means x is -4. All right, now I'm going to try something for letter C and letter D. Hello. All right, so I haven't been keeping my video on so far. I used to keep it on all the time when I made these videos, and then at some point, I think it was maybe a couple semesters ago, it just stopped working out of nowhere. So I got used to not using it, and then so maybe last semester it started working again. But I usually keep it off most of the time. Oh, now the bird's talking. But the reason I've turned it on is because I want you to see what I'm talking about. Hold on a second. Okay, let's try this again. All right. So the reason I've turned the video on is because I want to show you my visual for when I say squash the graph onto the x-axis, I mean like this. All right, imagine, putting your hands above and below. In this case, it would be above the graph. Put your other hand below the x-axis and squash everything onto the x-axis. You would end up with a big smudge along here, right? It would start at x equals -4, and it would go forever and ever to the right. And the -4 would be included. Okay, so the domain of this function is x is greater than or equal to -4, otherwise known as bracket -4 comma infinity. And then the range, my visual for the range is like this. Squash everything onto the y-axis. So if you were to squash everything onto the y-axis, it would start here because that's the lowest point on the graph, and it would continue forever and ever upwards. All right, so we're talking about y is greater than or equal to 2, also known as bracket 2 comma infinity. That's going to do it for section 3.6. That's going to do it for chapter 3. So we've got 2 chapters down and a few to go. All right, we'll see you next time.